Oh,
Well, I just have so much fun. There's a certain point in which you start to recognize the simple experimental fact that the only time you can talk about time and length is when you have matter. And you stop trying to make everything into a nebulous form of space-time that can never be measured without matter and energy. It really flips things upside down and opens up a lot of different exploration possibilities with a lot less noise in the math. Suddenly you're constrained on your math and you have to focus on saying, well, what is it actually doing? And right now it's very easy just to get lost into huge complexity, as I talked about in the last talk, that just doesn't go anywhere. And we've seen that. We've seen that, gosh, 45 years now, that expanding complexity and very little convergence. And it would be nice to have some simpler approaches. And I think that is very definitely a route. Take a sparser route and say, how is this generating all that? So it's a fun topic. And once you click onto it, it's hard to go back. I look at the way I used to think of physics, and it just looks so noisy. It's the same math in many cases, but it's a different perspective on that. And you say, yeah, but that's just what you're generating by poking it with a gigantic particle accelerator. Of course, you're going to get a lot of complexity. That's what happens when you blow things up. They explode. That doesn't mean that that's the everyday reality of what that system is. So it just gives a different perspective where you have a lot less infinities laying around. So it's fun. So what else is going on in Arlington these days?
we have a lot to join our third event. It's a pleasure to invite Terry. And Terry is a computer scientist. And so, Terry, when you're ready, let's start it.
Okay, let me get slides up. So the topic for today is smooth space-time is only a first approximation. What I mean by that is that we have a model in a standard model in mathematics where we look at the structure of space-time as a smooth, as just something that goes on to infinity. There's infinite variety, infinite detail that you can go into with any particular piece of space-time. So what I'm suggesting with this is that we need to move to a somewhat different approach with this, one that is more attached to the actual physics we experience. The particular point that I'm going to be hitting on with this is really a remarkably simple one, and it goes back to the original 1907 papers by Albert Einstein, in which you have a translation mechanism for going between coordinates in different inertial systems. So this presentation necessarily, I'm going to have to get a little more into some of the math. Some of this is here more for reference, but none of the math is complicated. In fact, it's all just algebra. There's no tensors or anything like that. That's not necessary for the debate.
Terry, are you sharing your?
Let's just start. Let's just start that one over from scratch. All right. Hello, everybody. Topic today is smooth spacetime is only a first approximation. The purpose of this is to look at some details of how we deal with special relativity that argue that we need to be more attached to physical mechanisms, clocks and rulers, which is what Einstein talked about entirely up until 1911. He never talked about Minkowski spacetime until after that point. Up until 1911, his only focus was on mechanical devices that would actually record time, that would actually express time, that would express length. And that turns out to be important because there are things you can do with that Einstein showed that you just cannot do with a pure mathematical abstraction, because the mathematical abstraction immediately takes you away from those measuring devices. So it's some really interesting history there too about why Einstein did this complete flip after 1911 from using clocks and rulers and complaining that he didn't understand what Minkowski was saying to it completely embracing Minkowski's space-time. And it has to do in part with the fact that Minkowski unfortunately died of appendicitis. And Einstein was really pretty grief-stricken about that. He was sad about what had happened with that. So some interesting history there, as well as just the actual physics. The first thing, and actually the central point of this, is there's an equation in Einstein's 1907 papers, which expand on his 1905 special relativity papers. And these equations give you a way for translating between two inertial coordinate systems. These are absolutely standard equations, algebraic. You don't need, you can express them in tensors and other ways, but algebra is quite fine on expressing these. And if you look at them closely, there is a small problem. And this is unavoidable. One of my most the two physicists I respect more than anyone are Richard Feynman and Albert Einstein in terms of their thinking. Just amazing to read their works and their papers. Nonetheless, you can still have small problems, and sometimes those small problems can turn into larger ones. The problem in this case is that the parameter for translating time is missing one element, and that element is the length of a physical system. The reason this is important is because a physical system attaches the equation to material objects in a way that the first equation does not. And that turns out not to be a trivial difference. And yet, if you don't add this one simple parameter, you wind up with paradoxes. You wind up with false results. And the results are pretty glaringly false. They're not they're just wrong. So the other obvious question, if that's so, then why has this worked so well for so long? And the reason is pretty simple. As long as you take a point-like approximation overall, if you have a spaceship traveling through interstellar space, if you have a particle going through an accelerator, the first equation works fine. Now, the reason is that you don't have any issue of length that is sufficiently significant to impact the net outcome. So you wind up with some odd little problems in how to interpret it sometimes, but the point approximation works very well. So there's a reason why these equations are very effective for what they do. But if you look at larger cases, when you have, for instance, two galaxies colliding with each other, if you have particles in a colliding accelerator where the particles are trying to be modeled at the quark plasma level, things change a little bit. And there are actually specific differences, even on that example of colliding lead nuclei, that you have to be a little bit careful about this very equation and what happens with that. It does make a difference, and presumably a predictable difference, although you have to get some very detailed data to do it. So that's, in many ways, that's the theme of this whole talk, is saying add one parameter, which is the length of the unit accelerated. And notice that includes history now. We're talking about not just a complete abstraction, but you have to have the history. And that leads to a number of interesting consequences.
Terry, sorry to interrupt. On that equation there, I'm a bit confused in terms of units there. You got velocity over velocity square. That unit doesn't seem to be consistent.
Velocity times x over c squared.
Yeah, in terms of units, you got v and the c squared, both the velocities, and it doesn't appear to be consistent.
You have v over c is beta, and then x over c has units of time. See what I'm saying? Okay, v over c gives you beta, so that's just just a factor. And then you have length over time, which gives you,
that length x is, so it's length over time.
Well, you have length over a velocity. You have length over the speed of light. So length over the speed of light, you're going to get length over time.
Yes, okay. Time. So you're converting basically into time. Yes, fine. Yeah.
Yeah, and this is a standard equation. There's no. I'm not quoting. This is. There's nothing unusual about that equation. So the.
Yes. Okay. It's okay. Just misread.
Okay. Yeah. No. The units do work out. Those that whole term on the right turns into time for both equations. By the time you do the, and there's different ways you can express it. This is just the usual, more compact way. I could have put down.
You're correct. You're correct. Sorry, I was my misunderstanding. You're correct.
That's fine. It's good to check on the clarification. Yeah, but the units are quite standard here. So the main point is that point approximation works really well. You don't have a theory that lasts over a century that doesn't work well, and it works very well. But there is an important qualification on that. And you see the fraying of the edges when you start talking about very large systems that collide each other or go at very high speeds. The first examples were these cosmic jets that they found, I think, back in the 70s, 80s, 90s. That started playing some interesting problems out when they tried to do those things. To address the elephant in the room, I'm just going to go point blank and say three particular problems that are all minor, but they're worth pointing out because they do make a difference. In some cases, they're not as minor as you might think. One of the most interesting, I remember when I ran a process that this is really interesting. One of the most interesting problems in the special relativity, the 1907 special relativity expansion, was Einstein puts in a little footnote, and his footnote says, the equations derived above, of which I just gave the example for the time equation, the equation derived above assume that there is no permanent change, no irreversible change to the object when it is sped up and slowed down. So this is kind of an abstract view of the object, that acceleration is a purely mathematical process, essentially what he's saying with that. It turns out, and I'll get into this in later slides, this is simply not a correct assumption. The Lorentz contraction that people think of as an abstract issue, when you apply it to large systems, like the example I always like to give is satellites in space, when you apply it to large systems, you physically have to move the pieces closer together. It doesn't just occur by magic. It is not something that's an automatically given. We don't notice it on Earth because when you get in a car, any compression is going to be so trivial compared to the velocity you're going at, you won't notice it. But when you start working with really large systems, the assumption that there is no physical change suffered by the system is physically and experimentally not correct. You have a differentiation. And the reason that's important is because you're making a distinction between the two systems as soon as you do that. If you have to compress one system, but you're not compressing the other system, you have created an event, a historical event that cannot be reversed, that distinguishes that smaller system from the larger system in which it's embedded. If you want a simple explanation for why we get twins paradoxes, that's it right there. Is most of the expressions, most of the explorations of the twins paradox fail to acknowledge that you're accelerating and changing and irreversibly altering one smaller system, the spaceship, while you're not doing that to the person back on Earth. People then get into all sorts of abstractions about when does the time dilation happen. I'll tell you when it happens. It happens continuously the instant you accelerate that system, and you can put monitors up to check that all the way. And that's not my own thought experiment, that's Einstein's. And yet we tend to skip over the fact that the way he came up with the twins paradox was to recognize that the time dilation effect is continuous, instantaneous, and is a result of the acceleration. You physically change the system and you do that. So that's a little surprising, especially considering Einstein was the one who explored it. That's how he found the twins paradox. But you can't just ignore that feature. And I say people get very complicated, like, when you turn around is when the time dilation occurs. None of that's what's going on here. It's actually far, far simpler. Accelerate, slow it down. You have to make a difference at that point. You also physically contract it. The Lorentz contraction happens at that point. And I'll get into this later about, well, what happens to symmetries? Symmetries are still there. This is what I love about this. The symmetries are still there. The Poincare symmetries still exist, but you have to constrain them in a very careful fashion. And that's why if you look at them within those constraints, but you don't recognize the constraints, you see this perfect mathematical symmetry. If you ignore those constraints, then you start getting these weird paradoxes. You start thinking like, well, who's slower than the other in the big picture? And that's an interesting result of this one small assumption that he made. Second problem. Two inertial frames can share the same coordinate origin without creating paradoxes. Now, this one's getting subtle. This is not something you look at and say, oh, it's obviously there's a problem there. There is a problem here because it's such an innocuous suggestion, and it's so reasonable. Einstein is going through the equation and say, well, obviously we can assume these are homogeneous equations. We'll have them the coordinate systems coincide at the same point. So you have x, y, z, and t all equal 0 at the same point in those two systems. You can't do that. This is what's so funny about it. It's such an obvious and easily assumed feature of the mathematics that you say, well, obviously I can do that in the physical system. But it turns out that that causes problems, and the problems are paradoxes that create things that don't exist. So you have to do something a little different. And this gets into that whole issue about why you have to have one more parameter if you want to get outside of that point approximation. So again, this is a problem. This was an actual mission. In fact, one of the reasons why I think Einstein got frustrated with some of this later was when he made this assumption, I don't think he ever went back and thought to question it. It is just such a straightforward one that it seems like, why would you question that? Okay, third problem. Oops. This one fascinates me. Einstein is notorious in a good way, is famous for getting rid of extraneous assumptions that you don't need. The assumption that length is the same, actually, seems like a very obvious assumption, and no wonder people thought that. Said, well, that's not necessarily true. The length can change, and you still see it the same inside of the system, but other people may see it differently. He did the same thing with time. He said that's another extraneous assumption that's being made. So in his, he has a wonderful little 19011. Well, that's well in the future. I think that's supposed to be 1911. I don't know how that zero got it now. I'll fix that later. And his 1911 paper, which is a wonderful little, it was actually a lecture that he gave, but someone transcribed it and took the notes and missed even an entire sentence at one point. But it's a great paper, and you can find a more readable version of it where I've added the figures that clearly he must have been drawing it at Blackboard, because he talks about it in ways that he's referring to something. So I've tried to give images that at least capture the essence of what he was trying to say. I feel sorry for the guy who was transcribing that lecture. He was trying to getting all the notes down and trying to get the figures also. He only got one figure. So, but it's great talk. And he makes this assumption. He just inserts it and says, well, Lorentz said that the speed of light can vary in opposite directions. And that's part of his theory. And Einstein looked at that. And again, I love the way Einstein thinks. He looked at it very carefully and said, you know what? Even if that does vary in both directions, you can't tell. So if the speed of light right now for you sitting in your chair is 1 billion times faster going forward and 1 billionth that time going slower going the opposite direction, they have to be ratios, by the way. And they missed that in some of the presentations on this. But you can't tell. There is no way that the physics allow you to detect that you have an asymmetric speed of light. And so what Einstein did was, and Einstein was very aware of this. He always defined the speed of light in terms of a loop. So he was aware of this, and he said, well, you know what? Since you can't detect it, I am just going to declare it to be the same. I'm going to add an arbitrary constraint. And so he adds a stipulation, which is exactly what he just got rid of. He got rid of 2 stipulations, and he adds a 3rd stipulation. The problem with the stipulation he added is that it messes up the relationship between frames. It's absolutely true that you cannot tell within one frame that speed of light is different in opposite directions. But if you do this on two frames, and you have a frame that's whizzing by you at high speed, and you look at its clocks, and you look at its speed of light, you see the same speed of light. But to you, the time is all messed up for the other person, that the time is very slow in the backwards in one direction, in the forward direction, and very fast in the backwards direction. And you see that. And if you want to, you can express that in terms of saying his effective speed of light is enormously faster in one direction than the other. Or you can express it in terms of time. It's either way. When Einstein made this stipulation, he inadvertently clobbered the ability to express that. And in doing so, it creates, again, kind of getting these paradoxes. You get these strange little problems that you can't deal with in a very straightforward way. Using Minkowski representation further hides that problem, because Minkowski space is great, but it also obscures this very issue because it just doesn't express it in the same way. Einstein talked about non-simultaneity. This was one of the most fascinating results Einstein came up with, is that your definition of things happening at the same time are not the same as my definition of things happening at the same time. And the idea of simultaneity has just fascinated physicists ever since, because they say, how can this be? How can people have different definitions of what is simultaneous? Isn't the world more organized or orderly than that? And he used this example of a train and lightning strikes. So you have two lightning strikes simultaneous, and he shows that even if they look simultaneous on the embankment of the train, they don't look simultaneous inside of the train. So Einstein was keenly aware of this and was the one who promoted the idea of non-simultaneity. Here's the weird thing. He never gave an equation for it. At least not that I've been able to find. If anybody knows one, I'd love to find out about it, but I have never found where he gave an explicit equation to say, and here's how you calculate the degree of non-simultaneity. And that is a puzzling thing, because he loved to put down the equations for little points like that, but he never did for this one. So what I'm doing with this is using his equation. It's easy to come up with this slope, this time per distance ratio. And the way you do it is you just take two of the points using the equation he provided, and you find out, well, what's the difference? What kind of rate do I have coming out with this? And the net result of it is that you have a quite simple negative relationship. So as you go in the forward direction, you find out you get a change in time. And there's no obvious reason why Einstein had this basically in the equation. I mean, this factor that comes out here really is the same factor that's in that equation. So it's an interesting little surprise that Einstein did not do that. And this derivation gives what I call the alpha factor. Good luck on picking at letters, but alpha seemed like a fairly safe one in the context of relativity. Of course, it's used in all sorts of other things in particle physics. But the alpha factor is just this ratio. So you measure so many feet, and you say, what's the time difference? And you find out there's a difference, so that the back of the moving object is going to wind up being older than the front of the moving object. I actually derived this for about 2 years. I used to talk about Einstein's missing homework, that Einstein missed this. And this is my derivation, which is much messier. And I remember I was surprised. I went through all this work. I was going like to the geometric work, say, how does this work out? What is that ratio? And when I finally came up with it, when I expressed it in terms of the coordinates of the moving object, where you take out the gamma factor, it was just minus the velocity. And I'm thinking like, what? All that, it just turns out to be minus the velocity? And yeah, so it was a very strange result. And I could not understand why Einstein didn't record that. And then I go back to his equation. I found, oh, he did record. It's buried right in the middle of his equation. He just didn't bother to pull it out and make it into a separate expression of that. So my derivation, like for 2 years, I unfairly said that Einstein overlooked that. He didn't overlook it. He just never wrote it down, which is in itself interesting. Why was there a mystery about that? he was the one who advertised non-simultaneity. He had to have derived this expression. He had to have known that. He was always putting clocks on everything. He put clocks here, he put clocks there, but he would have put clocks in the trains. What's the difference between the clock at the beginning of the train and the end of the train? I'm sure he would have done that. It's just the way Einstein thought. He always liked to explore those little nooks and crannies. But he never wrote it down. And that gives you an incentive to find a mechanism where you can explore this a little more carefully. The mechanism that is extremely useful for all of these problems is something called a light pendulum. It's just a form of clock. And a lot of what I'm going to talk to now, I'm going to go through some of this fairly quickly, but I just want to give people an idea that light clocks, light pendulums are a very handy tool for understanding spatial relativity at a much deeper level than just using the line only on the equations. Here's a 3D light pendulum. I like this thing. It's just, you have a light emitter at the center of a sphere. You have a pulse of light that goes out in all directions, comes back, bounces, returns, and goes to that. You calibrate this thing so that all pulses return at the same time. And when you finish calibrating, you get two things. You get a measurement of distance in all three axes in three-dimensional space, actually getting all the points in the sphere here. And you get a measurement of time. And that's a marvelous little combination because it says with one device, one compact device, you can measure the concept of space and time simultaneously within a single inertial frame. So these are useful test devices. Now, the other thing about this, since we're talking about velocity, you could also cut down the number of dimensions and go down to two-dimensional. And again, same idea, just you're ignoring one dimension. But the most useful one is where you cut it down to one dimension and keeping in mind that you're going to be moving this light clock in a particular direction. So here, starting at the bottom on this one, you have the same idea. You have a pulse, two pulses of light that go out, they hit mirrors, and they come back together. The distance that you're covering with that is a measurement of length. And the unit here, I call this a photon foot because it's very close to a foot. It's extraordinary close to 0.3 nanometers. So that's an even better way. So, but I use it just as a quick abbreviation for saying this is essentially one light nanosecond. And with the label PT for photon foot. So it doesn't matter what you call it. There's just some kind of abbreviation put down and not write a whole bunch of stuff every time. So here's what it looks like. You have that same structure. You have a pulse emitter, goes out to two mirrors, comes back, and then you detect that. When you synchronize those and make sure that the detections come back at the same time, you also have a measurement of length. This is what this looks like if you compress it down into a device. And my own informal name for these are javelin clocks. And why a javelin clock? Because it's a clock, it's shaped like a rod, and you throw it. You launch it in some direction, you make it go to the right, and then you see what happens. How does this change the physics of time, space, and time as measured by the javelin clock? By this javelin, it's also a ruler. It's a javelin clock ruler. So makes a very interesting, simple device for testing a lot of things in special relativity. You may have heard, or one of the things that Einstein did about defining space was he went to quite a bit of detail to define it in terms of time. And that seems counterintuitive. You think, well, why would you define space in terms of time? Well, space is, by definition, something that is not accessible instantaneously. It's the orthogonal to the speed of light. You can't touch all points at the same time. So what you have to do instead is you have to do a system where you can report that all these points are measuring the same time, and that actually winds up giving you a definition of space. So this is another thing. The middle line of this is really your definition of space for this particular light clock. The distance between those is measured in terms of, do all these points report at the same time? Einstein actually did this on deriving length contraction. The way he did it was he said you have a whole passel of clocks that have been previously synchronized. I don't show that step here, but you can go back to the paper and see the illustrations. This is from that same paper I mentioned earlier from 1911. Great paper. So he has all these steps in which you start with one clock, you synchronize a whole bunch of clocks to that one clock, and then you send this traveling rod through there and you say, hey guys, I want you to measure at exactly this instant, where's the front of that rod, where's the back of that rod? And then he goes through an interesting derivation to prove that you have to wind up with the length of the rod being contracted. And this is a very different way from how people usually think of how he might have done it, but his actual method relied heavily on this concept of simultaneous time, which he had to set up in advance. In terms of analysis, and this is a simple point that's worth emphasizing. And because I know I did this for years myself. When people think of two different inertial frames, it's easy to think of the moving object as having its own kind of space that it lives in. That, it has its own definition of time, which is absolutely true. And it's easy to think that you can't get into that definition. That is false. That is completely false. You can scan that thing, you can scan the daylights out of it. You can watch every step of what happens in the object using this definition of spatial or clocks in space. They just go through and analyze and say, well, where's the light beam now? Where's the light beam now? So you have this constant observation, and it means that you can take someone else's light clock, someone else's javelin clock, and you can analyze it in great detail and say, how does this thing look at a particular moment in time? If you use the abstraction that says, well, that's just off in a boosted frame, and I'm in this frame, and there the two shall meet, that doesn't tell you anything. And this is another reason why you won't see Minkowski space showing up in this. I'm just using ordinary three-dimensional space because that's the space in which you can do analysis. If you use the Minkowski representation, you're throwing yourself away from the analysis. And what we want here is to say, how does the data compare? What's the actual comparison between these? So you can do a scan. It's just like a raster scan of some object, just like do a LiDAR. Now, what happens if you move a javelin clock at a fast speed? Well, this is an exact representation of what happens if you move a javelin clock at 0.6 C, which is the same beta equals 0.6. So like units of C, beta, it's the same thing. So you have your emitter down at the bottom, you have your mirrors, you have the points at which the mirrors reflect the beam, and you have the detection at the top. Now notice, you've got Lorentz contraction, because down at the bottom, instead of this thing was originally 1 pt across, 1.3 nanometers across. Now it's 0.8. So you have a Lorentz contraction going on here. Also notice that at the top, when the eye at the top sees that time, that is also a Lorentz factor. That's the inverse of it, and you've got a time dilation. It's been stretched out a little bit. Now, the point I'm emphasizing this is once you accelerate a javelin clock, this is why I say there's no ambiguity about when the time dilation occurs. It occurs instantly. It begins instantly. The clock simply runs slower. Any analysis you're going to do is say that clock is running slower. Why? Because the light has to go farther before it can get back. You see that blue forward moving section there. It's just going to take more time. And there's nothing exotic about this. It is an accelerating system embedded in a larger system is going to go slower in time. So yes, you have your Poincare symmetries. We'll get into that about how they still apply, but you have to be careful about the constraints. The other thing I want you to notice in this is see how that brown line represents space as defined. Well, as space is defined by the person in the javelin clock, by the javelin clock. Time is defined by that blue line. So both of those are slanted. So you're not going to get a single view of the space representation. You're going to get a slice of it that's going to vary as you go by time. The other thing I want to point out, this is not a new figure. Minkowski in 1908, if you look especially at the trapezoid on the right with the two Q's at the bottom, that one is the same thing. Now, you can get some details about how you represent it. He does not show the light paths that I showed, but this is how he derived it. It comes up with the same kind of geometry. So this is actually an old concept, but you have to elaborate a little bit on it to make it more experimental with that. So interesting example of these trapezoidal shapes are these distorted outlines that you get when you send a javelin clock at a high velocity. In fact, if you look at the light paths instead of the mirror paths, you get this beautiful parabola, which if you look back is the same parabola that Minkowski drew. And you get these little areas, these little regions that show the lines traced out by the light path. I'll tell you another interesting little feature of these. Every one of those rectangular areas has exactly the same area. This is actually an invariant in special relativity. The times distance on these areas remains invariant no matter how fast you are going. So, and as it extends out, you get that parabola, you get the same lovely little design that you get from Minkowski's work. Now, if you want to get detailed, here's like the full gory detail about all the different features, how these things work, how these different features work out, where you get the units from. So it gets a bit messy, and I'm certainly not going to try to go through that, but I will point out one number here called R. R is the relativistic Doppler factor, which I found out belatedly, because when I found it, I called it the forward light path ratio. So it's the ratio of how far does light have to travel to get to the detector in the one system versus how far does light have to travel to get actually to the mirror to get to it in ordinary space. And this turns out to be a good number, this ratio of these light paths, for figuring out how these things work. But it also is something called a relativistic Doppler factor. I was going through some materials, and lo and behold, here's the exact same equation I've been using for the forward ratio. So R, relativistic Doppler factor, is an important number, and I would argue that it's actually more fundamental than the Lorentz contraction mechanism or number. If you want to go through, if you really want to go through all the details, this is I've got this available on my website. If you'd like to see all the different conversions you can do between these factors, the relativistic Doppler factors, a factor called rapidity is also very interesting. That is, you're talking about different logs of the relativistic Doppler factor. So a bunch of these, and I've also got the age gradient, which essentially is a version of velocity, and two variants of that can be useful for practical purposes in trying to measure inside of a system. If you're actually traveling in a system, traveler's gradient's a little easier to use. So this is massive overkill, but they're all pretty well checked out, and there's a Google equations version of these if you actually want to play and try some of these. So a lot of different factors you can bring up, with R being a particularly important one. Now, in some ways, this is just ridiculously obvious because Einstein already pointed it out. Yeah, if objects are seen as being asynchronous, it also means the object itself is asynchronous with the outside world. So if the train sees the lightning flashes as being asynchronous, then if somebody looks at the train, guess what? If you analyze the train in terms of lightning flashes, you will find out that the train is asynchronous. And yet we tend not to think of that way. Our minds jump instantly to a different viewpoint. We want to become the observer in the train and say, well, from inside the train, it's fine. Yeah, you can do that, but it doesn't help, because if you do that, you've immediately lost the analytical aspect of saying, well, what actually happens? Because you jump, anytime you jump observers You got to be very, very careful. People do that when they cross black hole barriers, by the way. They always instantly jump between one observer perspective and another. It's always dangerous in mathematical analysis. You should jump instantaneously without thinking about it from one viewer to another viewer. You don't want to do that. It destroys the ability to analyze. So if we go back to the simple realization that this clock is fully within our space, all the parts are there, it's going by, it's whizzing through an actual system. If it's a train, it's on tracks. So that's an obvious one there. If you got a Lorentz compressed train, it's still riding on the same tracks. And those tracks still have time attached to them from our system. So same thing here. You can always analyze these. And when you do, you discover that the object is not synchronous with itself. So if you watch somebody's head going by near the speed of light, you would discover that the front of their head is ahead in time compared to the back of their head. And there's something about that just doesn't, we don't want to think that way. You can't imagine being an observer and being asynchronous with your own mind. And yet that is exactly what the physics tells us, that in terms of the analysis from an outside observer, you can see this as a synchronous system. And you find out that the right mirror is too young and the left mirror is too old. And here I think we're starting to get into why Einstein didn't really want to quite, possibly he was just having trouble figuring out how to do this, but there's a problem as soon as you say that. Say, well, what's the actual numbers? But how much younger is the right mirror? How much older is the left mirror? Where do you get the numbers for that? This is also where that minor error I mentioned about the coordinate systems comes in. Because if you make the choice that Einstein made, you only get paradoxes. And that's one of the reasons why I think he may have backed off from talking too much about this, is he didn't feel comfortable with it. Does the internal asynchronous matter? Can you tell it inside the system? No, you cannot. Absolutely cannot. This is where the symmetry of inertial frames is just gorgeous. Every inertial frame has a perfect view of physics, of everything. It all works the same. This is exactly right. The trouble with relying only on that is it forgets the fact that all systems originate from some other frame. There is a history involved with this. And if you simplify your math too much and say, I don't care about that, you got to be careful, because in this case, it does make a difference. The origins of these systems makes a difference in terms of both their internal structure and in terms of how they behave to the outside system. So one particular example, and this is where I think people can get hosed with too casual of an understanding of space-time, is that if you accelerate to a high velocity and you have your own new view of the universe, your view does not extend or change the past that you had prior to doing that acceleration. You don't have suddenly access to some past that didn't exist before, which can be an intuition. If you're not careful, you can think that. You can think like, oh, it's the whole universe. I see everything in a different way. No, you're still bound by exactly what you saw before. So you want to be careful about the impact of origination on these different inertial frames. Poincare symmetries, powerful as they are, do not track that issue. And if your math is too simple to track the reality of what's going on, you want to have a more complicated mathematical system. It just means, the symmetries are beautiful, yes, yes, yes. And you can get really wrapped up in symmetries and not realize that they're not tracking the actual history, information, and causality. And if you're abandoning careful tracking of causality, you can have some problems. Point of this is acceleration is complicated. If you just think of it, oh, it's just the second derivative velocity, or it's just a boost. No, it's not. It's actually acceleration is one of the most interesting features of physics. And I could go on about this in terms of the quantum domain. My goodness, There are some interesting things that can happen in the quantum domain with acceleration. But for this one, on relativistic, what happens is you can't co-locate, you can't do what Einstein described in 1907 without creating false stories. You wind up getting a paradox about who's doing what when, and you wind up creating views of the past that do not correspond to any actual thing. You set a clock back to a time and say, oh yeah, well, this clock is 1 year in the past. So do you have access to 1 year in the past? No, I don't. I just set the clock 1 year in the past. You get that kind of conflict with this. Where I think acceleration, the most fascinating part of acceleration, which is related to that, is that you get a conflict on two fundamental definitions of time. And by fundamental, I mean, right, yeah, you can't get much deeper than these two. The first one is experience time. How much time actually elapsed? You're continuously observing it, and there was no gap. You might see a slowdown, that's fine. You can have slowdown, speed up, that's fine. But you still see a continuous elapse of time. So you have an experience time, and it turns out when you accelerate a system, that has to break. Something has to break. The other one, the experience time, is interesting, but the other one is physics time. And this is even more intriguing. When you accelerate a system, you break physics time for a while within that system. It takes a while for the system to return to a state in which you can do, as Einstein described, measure any aspect of physics and find out that all the physics is exactly the same. It takes time to get back to that state. Now think about that. You don't instantly get measurable classical physics when you accelerate a system, especially if the system is large. It takes time before you can return to full analytic capability with a full definition of space and time again. So, but that is deep, because when you talk about classical physics time, you're talking about quantum physics. You're talking about the definition of a point particle. You're talking about some really profound aspects of what we think of as just standard physics turn out to be shredded for a while after you do an acceleration in terms of being measurable. You can always do an abstraction, but let's stick to just what's actually measurable. It takes time to recover that. This is saying something important. And this is an issue I continue to explore, but it says something important about the impact of acceleration on that system and the system around it. When I say it's interesting, for instance, I would bet you this is related to the whole idea of quantum collapse. When you have this conflict in time, to the micro scale, what's happened to the micro scale, this is going to play havoc with some of your definitions of time at that level. So let's look at this lost time issue a little more carefully. As it turns out, this is not what Einstein said. So I'll start with the one that changes it. If you, instead of setting the coordinates to be 0 over at the left side of the train, so they also have x, y, z, t, x prime, x, y, all the prime, you have both of those set to 0 at the left side of the train. This is not what this one is. This one says, let's do it a little differently because that doesn't make sense. So you put the 0 setting at the right side of the train because you have a negative time gradient, negative alpha. And then you have to go back to the left. And when you get to the left, you see that you have to add time to your clock. And this is distressing because you go like, I didn't experience that time. There was no time. I didn't see any time go by. I just reset my clock. It's just exactly like daylight savings time. Spring forward, you just set it an hour ahead of time. You can do it, but it's unsatisfying because you think like, well, how did that happen? Why didn't I have to do it? Why do you have to do this? Because until you do that, until you have finished that, you cannot come up with a self-consistent definition of either time or space. Your new inertial frame is at a different angle in space and time from what it started. And you have to do this in order to recover the idea of classical precision down to the point particle level that you wanted. So it's not something you can just skip over. You have to do it. If you have a material body that's being accelerated, all this gets taken care of for you at the atomic level, because the atoms jostle themselves, they figure it out pretty much on their own. If you're doing it with satellites, no such luck applies. You have to do an explicit resetting of some of these. The alternative, and here we get back to what Einstein proposed, and this is why I say that this seemingly completely minor, mathematically obvious thing of saying we'll just set the coordinate systems identical for the two systems does not work when you accelerate a system from another frame. You have to have a history here. And what it does is you have to reset the time clock backwards in time. And this is where you get your issue of false time. You don't want to do this. The other alternative is better. It's annoying, but the other one at least does not create false time paradoxes. This one does. It says that I had 0.6 microseconds of time that I didn't really have. And by the way, units here are kilophoton feet. So, same idea. So it's the 0.3 kilometers instead of 0.3 meters. So this is interesting. Who would have thought it's not obvious that such a small choice would have such an odd impact on how you measure time in these systems. Here we get into a full model of what is acceleration really. So again, forget boost for a while. Instead, look at this in terms of, and you can slice this and dice this in different ways, but 4 different steps. First, you have to select. So I did a little alliteration, select, squeeze, sync, and send. So it just makes it a little more memorable, but also it's pretty apt. You have to select an actual length of an object. You have to say, this is the system I'm accelerating. It's not just, I just can't say that it goes beyond that. I have to say, no, this is the pieces of matter that I'm going to accelerate because I can only define my new spacetime using that set of matter. So the next one is the step. And again, this is counterintuitive. You'll see all sorts of complicated explanations about why, if you have a rocket going at the speed of light through a barn and you shut the barn door here and shut the barn door there, and it gets very complicated. The simple truth is the reason it gets through the barn is because you squeezed it before you ever sent it. It really is shorter. This is not some mathematical abstraction. You had to squeeze that sucker. So it's smaller than it was and go through the barn fine. So it's a refreshingly blunt way of describing some of these paradoxes. And yet it's not that the other ways of doing it are incorrect. They're actually quite accurate. It's just there's a simple way to think of it if you recognize that this is an actual physical step of squeezing the system together. When you're accelerating a car, no problem, because the acceleration of the car is gigantic compared to the amount of length of contraction you use. When you do satellites, not so easy. The third step is the one that, as far as I can tell, Einstein, I don't think he missed it. I think he just kind of felt uncomfortable with it because of that decision he had made earlier. So he couldn't see how he kept getting these negative times in the front. So instead of doing this, he just left it at the back of the train and then just kind of said, yeah, something happened. So it's really fascinating how he did not address that particular issue. So to get one that is at least not paradoxical, you have to add a parameter. You go to that previously selected length. You set the t equals 0 at the front, and then you have to reset the clocks behind. So you get a time delta as you view it from the acceleration. And then you finally add momentum everywhere. If you can have things like every little car has its own rocket, or if you want to do something like that. And again, with satellites, that becomes more realistic. These steps can be mixed and matched. You can, for instance, reset the clocks first with a slightly different sequence. You can compress them second. So there's some variability in how you do that. You can get more complicated schemes, so the compression is more efficient. There's a lot of parameters that you can play with. But this sequence captures the major differences and the physical steps that you have to do to accelerate a system to create a self-consistent definition of space-time within that object, one that will see the same quantum physics, will see the same particle physics, will see the same everything. You have to go through these steps. And that's remarkable. What to have to go through this much of a physical procedure to get to the point of having classical physics recovered and measurable. You can always say, well, it's there by default, but if you want to talk about measurable physics, as Einstein did when he gave these examples with the clocks, you have to go through this. Here's the example for the interstellar satellite network. And I like this one because it's the same as previous figure, but it points out that there's very real issue on how you do this. You can't just assume that satellite's going to just suddenly magically go over 0.2 light years. That's not going to happen. You have to send it. You have to accelerate the satellite on the right, send it in farther, and compress the whole system before you can start getting the thing working. Oh, and you're going to have synchronization issues, which could take you a full year to resynchronize. You see how this is getting messy? So after you do that, and after you reset the clocks substantially this time, and with a huge jump in the satellite on the left, after you do all that, and you add your momentum, again, you can mix and match these things. You can do them in different orders. After you do all that, you finally recover physics, standard physics, particle physics, quantum physics, field theory. Field theory. Isn't that interesting? Field theory doesn't work until you recover this, which says something about field theory's relationship to matter that's also very interesting. So there's an example to say that when you talk about special relativity, don't just talk about a boost. There's a lot more going on, and the steps do make a difference. Now, let's get back to the other issue. I love this one. Terry, Lorentz contraction is symmetric. You know it's symmetric. And I do, and I agree completely. Not only agree with it, I think if anything, I'm even more enthusiastic about it. If you have an inertial system that you have accelerated, I say that the physics is so absolutely identical. Don't tell me that it's going to reach some upper limit. And no, you can accelerate to 99.99999% of the speed of light. It doesn't matter one lick. You're going to get exactly the same physics in that system after you've gone through those steps I mentioned, which are hard. It was a big object, but if it's a small object, like a proton, you can certainly do it at that level. So it all works. And those symmetries say that Lorentz contraction is symmetric. So you've often heard, or maybe you've thought, that if you are in a spaceship and you look at the outside universe, it's going to look flat as a pancake. Did you know that's not true? It's absolutely not true. But people talk about that on the assumption that the Lorentz contraction is fully symmetric, and they assume that that's true. What you actually get is a very interesting phenomenon in which the forward appearance, and of course there's a whole equation to go from forward to backward, but the forward direction is compressed, is contracted, not by Lorentz factor, but by this Doppler, relativistic Doppler factor, 1 over the R, 1 over the relativistic Doppler factor, which you can see it's a very simple expression. And I think I forgot my square root on that. Yes, I did. There's a square root of that. So my apologies. I'll get that fixed in a later copy. So 1 over the square root of R, and that should be square root of the quantity that's divided. Object lengths behind are multiplied. They're stretched. And you think about it, is that really that unreasonable? Because the light is chasing you from behind and it's being jammed into you from the front. And light is a measure of distance. So why should this be a surprise that things in front are compressed? So that's what you actually see, is you see something much more complicated than what you had before. Now, I said Lorentz contraction is symmetric. Where is it symmetric? Inside your spaceship only. When you have an object, such as a particle that passes through your spaceship, let's say you have a muon that's decaying, as long as that muon is inside the domain of your spaceship, you will see it time dilated tremendously. You'll see it going like it goes right through, and it's just exactly what you would expect. because your physics rule inside that spaceship, your physics and your physics only rule for that set of matter that is defined by the spaceship and you. And you will see the time dilation expected. You say, well, then how is that possible? Because that muon can't possibly have lasted the entire duration of your trip. Well, that's because go back to what I just said. In the forward direction, it actually decays faster. In the backward direction, it actually decays slower. The two approach each other. There's a Lorentz factor that become almost the same after a certain point. So those ones go slower, but it's only in the domain of your ship that you see the Lorentz contraction that you expect. So fascinating little effect. Another way of looking at that same issue, and I use this for other reasons. So I also use this diagram for quantum mechanics. When people talk about the impact, instantaneous impact of entanglement, there's no such thing. The only thing you see is a radiating circle of influence of where you could have touched something on the outside. And until that circle touches a distant spot, it doesn't matter if the particle is entangled there or not. That's the only time in which that point sees a change. So entanglement is not what people think it is. There are correlations, strange correlations, you bet. But you have this circle, speed of light circle that you have to respect. So that's quantum side. This side, I'm just pointing out that there's your compression effect right there. It's like a cone leaning to the right. It's not quite a shock wave. Shock waves, when you go beyond that, I've never seen a really good term for these sub shock waves, where it's almost a shock wave, but not quite. But whatever you might call it, it just looks like a cone that leans closer and closer. And then the front gets more and more compressed. And you get the gradients until you get to the rear side where you get the stretching. So another way of looking at that same issue, backward and forward compression. But Terry, time dilation is also symmetric, doesn't it? Isn't that also a problem? Well, yeah, okay, the same thing. Clocks, anytime you hear about blue shift, here's a simple thought. Maybe it's not that simple because it took me a long time to figure it out. A light wave is a clock. If it's circular polarized, it looks exactly like a clock. And when you have something blue shifted, it means the clock has been sped up. So we talk about time dilation as if it's only time dilation. That's not what you see from a spaceship. You see time speed up. I don't know what the opposite word of dilation is, but you get a speed up in the forward direction. Is it a real speed up? You bet it is. Because if you blue shift all the way to the Andromeda system in your spaceship, when you get to the Andromeda system, you will find it is exactly the time that the blue shifts told you it was at. There was nothing hypothetical about it. It was a time speed up in that direction. If you look at the rear direction, you get this time slowdown. That one's hard to judge because you're not actually making contact. Until you make contact, you can't, you have issues about what's going to happen in your reverse directions. But the speed up in the blue in the front direction, you bet. You've encountered those light waves. They are little clocks running through space. Every time you hit one, that time is gone. It's another way of saying that you're actually running slower than the rest of the universe. So again, it gets back to this thing that when you speed up a spaceship, there is a real continual time dilation going on relative to the gigantic frame that did not accelerate. And it's going on all the time. Once again, objects passing through your region, like a muon, got some spontaneous muons degenerating quickly, they're fine. As long as they're created soon enough to get through to your spaceship, inside of your spaceship, they will look time dilated. Here's a little figure I made, a little article. I had fun with it, just talking about what would Einstein see if he actually went into a machine that was traveling at constant speed of light. And the Einstein, the outside, would see exactly what he and also Lorentz predicted, which you get a time dilation of 1.25. But the guy inside the clock sees exactly what I was just talking about. He sees blue shifted clocks that are running faster in front, red shifted clocks that are running slower behind. And guess what? If you average the two, you get the Lorentz factor. Lorentz factor is not fundamental. It is an average of the relativistic Doppler factor and its inverse. And it's not an accident, it's because when it's going through your particular train or ship, at that point, you're seeing both effects at the same time. You're seeing one in one direction and one in the other direction. So if you have a light clock going on there, you'll see literally these two effects being broken into two parts, and then they average out to get this. Simple experiment, well, you can't really do this, but unless you got a very fast car, but time dilation, we try to make time dilation too complicated. It's a race. If your object is moving very fast, then it's going to take light a longer time to cross the path to get to the object in front. So it doesn't matter whether a lens compressed on your system, you've got your phone, you've got a detector you're doing there, it's just going to take longer. That is the essence of why time dilation occurs, is you've got a race in the forward direction against the speed of light. Continuous, doesn't relent, and starts the moment that you start accelerating at its high rate. But it can happen for conceptually very simple cases. Now, the point of acceleration, and when I say that space-time is more complicated, once you attach space-time to units of matter that even not only are finite in size, but they take a little time to kind of settle down. They can take a very long time to settle down and start producing normal physics again. Normal, it's how you define, but classical physics, classical point-like metrical physics does not emerge, including quantum field theory, including quantum mechanics, including you name it. All those forms of physics, as we measure them normally, don't emerge until you get this consolidation of that small unit. But once you got that, everything is the same. So that necessarily breaks up the idea of smooth space-time. Einstein's idea on the left, that everything could have a shared origin, kind of breaks down. You get this tilting process where you wind up things having a different definition. So this diagram here, I'm kind of so-so on this one, it's too complicated. This actually gives the idea better. You have a cone. In fact, if you think back to this one, where you have cones moving, you have things moving inside of other cones. That's kind of what this is. You're saying that you have cones. Each of these smaller cones is in motion inside of the larger cone. They never get outside that cone. They're always bound by the cone. That's incredibly important in terms of why space-time seems coherent at large scale, is because you have fractal restrictions. Fractal in the sense that you can do lots of variation in the details, but you can't get outside of the branch that you're on. And this is what's going on with these little matter cones, have their own definitions of physics. Each accelerated unit has its own definition of physics, has its own little light cone, or things that it could influence with that definition. But those definitions never they can approach it, but that boundary is growing at the same rate that you're growing, so you never reach that boundary. You always have this constant inclusion of the different domains inside of each other. And that's powerful, because that's why we can look at the universe and say, like, wow, it seems like it's all one giant space-time. Because in one sense it is. There's coordination in the galaxies and on large scales that is sufficient that we have this broad fractal definition of what time is. But then you have a lot of details as you go down farther. Now push that out far enough, and I would not be surprised if you see some problems with that. It's one of the reasons why I'm not very interested in dark matter, dark energy issues these days, because I think until we get this figured out a little bit better about how matter instantiates space and time at those scales, I think we're going to have trouble getting reliable definitions of what we even mean by dark matter and dark energy, especially dark energy. So more work needs to be done on that. But I love this idea that it's all constrained, it all has a certain coherency, but it also, each one is its own definition. You have a lot of power in that. Now, last month, I talked at length about the idea of sparse interpretation. For those of you who were not on that talk, it's a very simple idea. The idea is that the universe has a certain number of persistent, stable bits, mostly captured by particles like fermions. The number of bits is mass dependent. The number of bits is finite. And when I say bits, there's actually there's a distinction I would make. There's persistent information, and then there's actual bits, which are a little more complicated version of that. But either way, you have only so much persistent information that is determined quite nicely by the total mass energy of the universe. Then all of the domain where you talk about Planck scale, where you talk about smaller units, all of that is created by interactions. So you take a proton, it's sitting there, it's minding its own business, it's very, very happy. It doesn't show any obvious structure. You slam it with an electron at a gigantic fraction of the speed of light, and all of a sudden all sorts of details emerge. Instead of saying that those details were there all the time, a sparse interpretation says you're creating those details according to a set of rules. The rules are what matter and how you react and how you respond. But the details were not there until you did that. And this is fairly radical in the sense I'm saying that superposition is often used, like superposition of electron orbitals as actual orbitals of actual electrons is not a good picture. Because those electrons would take infinite energy just to create one of those supposedly components or components of the orbital. So this is one that says when you see an electron in a hydrogen atom, that's about as small as the electron's going to get. The electron is something a little bit different. It's not a particle, but you can tie it down to a very tight package that to us, until recent times, looked like a particle, atomic scale. But it's a different way of looking at physics. And it's very addictive once you get into it, because realizing every time you look at a problem, you say, how much energy did you add to say that? And you always say, like, some tremendous amount. And that should be a warning. That's saying that, are you looking at it in terms of what's the minimum number of bits that could account for all this complexity? And that's an interesting problem, because then you start looking at that. This whole idea of matter creating spacetime works very much with that perspective, because it says each system of matter literally creates its own definition of spacetime and physics down to the quantum, down to the level of quantum chromodynamics, the whole bit. Granted, some of these pieces we're doing fine without you doing it, but if you want to measure it, you're the one in that system. You set up that classical like physics in that system. So this goes together very well with that. It's just saying that space-time itself is an aspect of this sparse interpretation of physics. It's literally being created by those persistent bits. And this is also, I like this the most, it says that the standard model of physics, which has been around for a long time now, is extremely successful and very well tied down in terms of its predictions, but unsatisfying in terms of some of the details. It says that that is actually at the top of physics. Literally, the idea that things like special relativity and general relativity are not things that are out there creating the standard model. It's the other way around. The standard model is using some kind of physics we don't understand well. We really don't, because we've been trapped in this thing about looking at the chaos first. But it says that the standard model is based on some physics, and from that emerges these concepts of space, of time, and even of general relativity. One physicist, and Piotr, I don't know if you're out there, I hope you are, but maybe I'll send it to you later. A physicist who's done some marvelous work on just this issue is, and I can't pronounce it, Piotr, I'm not even sure I'm getting his right name. Yeah, marvelous fellow. But has explored this and looked at this idea and said, maybe we're focusing the wrong idea. The Planck scale, for instance, Planck scale energy, he made this argument. I never thought of this was an interesting argument. Planck scale energies are actually massive. They're plastic. They're like, the size of objects in terms of the total energy. He's saying that doesn't seem right. The balance seems to be more at the hadron level. So he has explored this idea that the hadron level is related to the idea of space-time. And I've explored the same idea from a different angle when I do some like those cube figures I do about how hadrons relate to each other. The fact that we have three colors and the fact that we have three spatial dimensions, I would strongly hypothesize that that's not a coincidence. There's a connection going on with these things. And this is where physics could really do some interesting exploration, is getting into this idea of saying if matter is always creating space-time, then how is it doing that? And what is actually below that? So it's into some interesting issues. What is space-time? Now, if you follow this viewpoint, both of the sparse viewpoint, that there's only so many persistent entities that we don't understand very well, but they're highly conserved, they're not easily destroyed, they're not point-like. The whole idea of pointiness is a transient condition. If you release one photon from any kind of device, that photon immediately stops being anything remotely like a particle. It is, by all accounts, by all experiments, a wave expanding at a very large rate, and then it winds up being pointy again. To say that that's one of the persistent problems of physics is an understatement, but part of the resolution of that is going to have to do with this idea that we're not understanding the non-point-like, non-spatial physics that's going on beneath, in which the photon is just perfectly happy with what it's doing and is not about to destroy itself until it gets to the right set of conditions. But at that point, it starts looking like something point-like. So a lot of these point-like things we see in that classical world, point-like is easy. As soon as you get down to the small scales, it starts getting really hard. And you have to observe the thing continuously, like in a fog chamber, to get it to behave point-like. Space-time has some kind of relationship with Pauli exclusion. If as soon as Einstein said over 100 years ago, you got to have rulers or you can't measure space, he really pretty much was saying invoking Pauli exclusion. Isn't that interesting? Because the only way you can make a ruler is using this principle of Pauli exclusion, this idea of fermions that reject each other, and in doing so, create a space-like concept. And then as it gets more complicated, you get these extraordinarily stable relationships that we then expand into our definitions of space. So numbers count on these things. If you have a lot of matter, you can get a very smooth definition of space-time. If you don't have much matter, that gets interesting. You start saying, like, how much space-time can I create with just, say, one electron? Or how much space-time can I create with 3 quarks? Piotr explored that thing. He says he thinks the inside of a hadron, this is not the first one who's talked about this, the inside of a hadron is not what we think it is. It's not ordinary space. We can impose that perspective on it, but it's something simpler, not as complicated, and I think he's really onto something with that. So the other thing, space-time, I would argue, is hierarchical. It has fractal self-symmetry. You have groups of matter that work together and create coherent definitions of space and time. But then you get new subsets moving within that, have their own definition of space and time. And the final point, and I just can't emphasize this enough, if you don't have matter, you don't have space-time. And you can, and I mean that in just the most literal fashion possible. What are you going to measure it with? You can say that space-time is matter, and I guess that's one way you can argue it, but the bottom line is you get this curious thing that you keep talking about measuring space-time without any instruments with which to do that. And this also gets into the issue about the density of the vacuum. And if you listen to my previous talk, absolutely, I'm on the side of saying that the vacuum is exactly what people thought the vacuum was for millennia. It's nothing, just absolutely nothing. There's no boiling, frothing, Casimir generating force out there. That only happens in matter, and it's strongly limited by the matter, which is a really interesting aspect that even Casimir noted indirectly. So space-time does not exist without matter. And that's a big flip from, it's very easy to go the other direction. And I always thought in the other direction complicated too, because why would something as complicated as space-time be fundamental? It is really complicated. How do you get that complicated set of relationships just spontaneously or exist? So having them attached to the matter certainly helps spatial relativity, and I think gives a more coherent view. So this gives you an idea that space-time is a bottom-up process, and the idea of space-time begins with a standard model, all the exclusion of these other factors, cyclic phenomena, or what make clocks possible. Constant self-observation is how you get this illusion of particleness, but that's also a huge part of why this works, is this whole idea of self-observation. And again, for folks who don't know it, for me, observation is not something magical. It's just bumping. It's about as unmagical as you get. It's acceleration. Every instance of acceleration, in part for some of the reasons I've talked about here, the fact that any acceleration introduces conflicts in the definition of time at a minimum, that's pretty good right there. Acceleration is critical for making things suddenly wake up and say, oh, I'm part of this system and I'm supposed to be here according to the rules that I've been following. You do that enough, you get very self-consistent definitions of things that look particle-like, but they're never really particles. And what's going on beneath is ill-formed and doesn't align with our usual concepts of particles or waves. Those are both hyperclassical concepts. So if you don't have enough of these entities, surprise, surprise, you get uncertainty. Why? Because of an infinite number of universes infinitely competing, infinitely all the infinite time? No, because you don't have enough resolution, you don't have enough details. If you look at one pixel on a screen, you don't get much information out of it. That's all this is. So I think we've loaded quantum uncertainty into a far more complicated topic than it needs to be. And space alignment is a variability in this. So if you look at, here's a figure, this is just kind of throwing out the idea that if you work this out, you get a breccia. A breccia is a kind of rock where you have these clasts, these little chunks of different definitions of space-time. I think something like this is a better view of how the universe works. And this is why I think if you look in the large scales of all these cosmic filaments and these strange things going on, I think we're seeing something more like this. You're just getting different competitions, different definitions of space and time that are sort of keeping up with each other, but after a certain point, they start losing it because they're so far away from each other, and the matter ratio to empty space gets so high that they start getting string-like, they start getting sheet-like, they start losing dimensionality, they start doing strange things. I think a brecciated universe is probably a more interesting path for figuring out where some news might come from. And again, this is a huge scale elaboration of that, but you can't get away from the fact that even in those smallest examples, going all the way back to Einstein's equation, once you have that length parameter, you have attached it to matter. And once you attach it to matter, things like this can happen. Oh, and quantum superposition. This is something, if you're creating space and time, it gets a whole different twist on some ideas of superposition. The biggest one is this. Many things that we call superposition of state are actually superpositions of space-time, meaning that we're playing games with how we create space-time locally. And those games look like waves. And what's really going on with the cat dead or the cat alive is to me, that just seems like an incredibly simple statement, but I'm a little biased to that. The cat either dies or it lives. It just does. We've exaggerated these quantum wave functions to places where they don't really apply. And then the cat, yes, it may have started as a quantum event, but the cat self-observes. It either dies or it lives. But this is an important qualification. If you can keep that cat totally, completely isolated from the rest of the universe in terms of information, which is the credit, the way the universe talks to itself to define space and time. If you can keep it isolated, then it will be capable of doing these interference patterns in terms of space and time. And what's really going on here is you're messing with the definition of space and time. it's not, it's not really going through, we need to understand this better. And it is that the physics underneath this don't respect our ideas of travel. Not the same way, not the same way we do. And we need to understand that we're just reconstructing a path, a space-time path after the fact, and it doesn't always work. Not when you look at this deeper physics going on. So, as Schroeder intended, dead cat, live cat, no, it either dies or it doesn't. But keep an information barrier, it gets interesting. Now, here's one, since I'm beating on this thing, I keep talking about physical points. A definition of a point, the very first definition Euclid gives of a point is that which has no part. That's actually kind of uninterpretable, but if you look at it carefully, what he really means is if it has spherical symmetry and you shrink down the smallest size possible, that's pretty close to that, what he's saying. It has no part, it has no information on it, it has no additional location to it. So there's a clue right there. To actually implement Euclid's first definition, which is supposed to be the most trivial part of his entire works, you have to use a calculus type condensation of a space, presumably of 3 dimensions, going down to some infinite limit. That should be a warning right there. It's saying that what you're actually doing is following a set of rules that have a nice asymptotic limit, but they don't actually get there. And in physical reality, they don't get there. You can take the electron and compress it down to a point as close as you want, but it fights harder and harder as you go down. So when you talk about a region of space having definitions of physics, classical physics, points are part of that. Electrons are part of that. And in fact, if you look at an electron that's moving by you at high speed, or if you look at a definition of a point, then it fails to be a point anymore. Why? Because it's elliptical. It has to be. This is a real physical change in terms of how it works. So you get changes in the conformation of the point, and you have to look at it. If it's a disc-like or it's an elliptical shape, is it still a point? And the answer is probably no. So the very definition even of a point in mathematics is dependent on having a self-consistent definition of an inertial frame. And I find it fascinating. It says that math has a deep tie all the way down to Euclid's first definition to the idea of a material moving frame with all of these properties that you've collected. I'm pointing out about distance, just a quick note on that. The earlier slide said that when you look at a distance, you're actually looking at times or clocks and issues like that. Every time we talk about a distance, we're using a rather complicated abstraction in which you have an assumption of stability across time. The ruler was there, the ruler is still there in the future. All these things depend on an enormous amount of complex material persistence. And without that complex material persistence, the ability to make a ruler, you really don't get that. So there's just a quick comment on that. It's trickier than it might seem. Oh, do want to get into this one. I thought I added okay. This is supposed to be a Van de Hoof antipodal black hole momentum state, which was a fascinating little bit of work that Gerard de Hoof did based on some earlier work, about saying that instead of black holes having white holes in some other universe, he had and I've forgotten the name of the researcher. My apologies to her. She had done this like decades before, but they came up with this idea of antipodal, which is just a really complicated way of saying that eventually, when something falls into a black hole, it just comes out the other side. And I like how you can get very complicated in lingo, but that's all antipodal means. It means that eventually it gets there. In the details, though, what happens is it turns into a complex momentum state on the surface of the black hole. Now, that leads to, if you think matter defines space-time, guess what? You can't have black holes quite as you usually think of them. you get something more like this. And I called it an asymmetric orbital scale. Yes, I think that was from a previous, I might change that acronym at some point. There is a really interesting different interpretation of a black hole if you define curvature of space as being a function of matter, which is this. Imagine that the center of the black hole is a definition of space-time that has been incredibly magnified to the point where nothing can exist in it anymore. It's even a single particle is excluded because space is so huge inside of the black hole that there's just not room for everything. This gives you a very different internal structure of a black hole, but it also gives you the same kind of event horizon surface that you see, especially see experimentally, on the top. So this is a very different way of looking at it. So the whole idea of a singularity just disappears. You instead get a really interesting kind of hypermagnification of space-time concept by the very, very dense matter at the top of the event horizon. Now, when I said experimentally, I meant experimentally. There is evidence that is just fascinating that when a star falls into a black hole, that on multiple occasions, remnants of it emerge years or even decades later and then continue to do so. That's not what's supposed to happen with a black hole. So that is a very different interpretation of what happens with a black hole. So it's an interesting paper. I have not seen follow-up work with that, but I think they're on to something there about what we think black holes are doing, what they're actually doing is different. This whole momentum issue, angular momentum issue, is really important when understanding black holes, and they seem to be hitting some experimental evidence that the internal structures are more complicated than we thought. On that same thing, this is just one example where you could go with that. When a star falls into a black hole, it winds up getting factored in terms of momentum. Think of it as being turned into an almost pure momentum state. So you have angular momentum is what the black hole wants, and the linear momentum is something that it discards. So this is a different way of saying that as you get the green arrow coming in, it gets broken down into the blue circle angular momentum, because black holes are ferocious on amplifying the orbital impact of angular momentum. But then it's got that other component that says like, yeah, I don't want that, to get out of here. So a very different way of interpreting something like that. Just an example of where taking matter as the origin of space-time gives you different ways to explore some very interesting phenomena. One last one, the same one, supernova type 2 core rebound. It's always been a bit mysterious. Like, how does this thing actually collapse and then bounce back so ferociously? Well, if a black hole is actually not a singularity, but it is a resistant chunk of hypermagnified space-time in a very small unit, you're going to get rebound. So it gives you a very different take on that one. You're going to get accumulation of the matter around the perimeter, but you also get a powerful resistance to anything truly falling all the way into it. The previous result that I mentioned, where you have stars popping back out in pieces years later, kind of goes along with this idea, because it's saying that, oh, it's harder to fall into a black hole than you thought. You can get slowed down, but it's not as easy as you think. All right, wrap up. Math is great, but simple math is often just that. It's too simple. Pointary symmetries are beautiful, but if they don't track the actual sequence and all the complexities that go on with what you're doing, then you want to examine whether you need to have a more complex model. And I would say that in the case of acceleration, we absolutely need a more complex model. The idea of reducing everything to a boost. There are certain cases where that's useful and it's very handy, but it doesn't tell you anything, especially if you're trying to understand the deep details of what's working. So the part of physics that I think is the most fascinating and probably the most productive, assuming that what I'm saying is correct, if you go on if you buy the idea that Sparseness is a good way to go, by the idea that space and time are created by matter rather than vice versa. If you follow that route, then it says there is a whole domain of physics that we have barely touched. We glance off of it when we talk about quantum physics and entanglement, but only in a very clumsy fashion. A term I've used a few times in there is nirakar, which is a Sanskrit term for formlessness. Whatever the physics is going on below this level, it has endurance, it has persistence after a point, but even the persistence is an emergent property. There's some combination of these things that wind up giving us this marvelous set of classical physics capabilities, but there has to be construction there. And it's a hard domain to think about, because if the first thing you throw out is space and time, then you go like, how do I analyze anything? And it's a good question, but it also is one that you want to look at more closely. Are the principles that hold? Absolutely. Conservation is certainly a huge, huge factor that never seems to vary. So the conservation of various quantum numbers is just a resolute part of what it is, whatever this underlying physics is. So there are some starting points, but the idea that your classical ideas of space and time emerge from that, but it's going to take some work. But this is also where I think the most power for issues like quantum computing comes from, because whatever this underlying physics is, that is neither waves nor particles, nor exactly what we would call quantum, but something really more nebulous than that at this point. That has potential, and I think it has some powerful potential. Biochemistry seems to make some kind of use of it, because biochemistry is always calculating things we can't do. That's why it takes us gigantic computers to model one silly molecule. So there's some potential there. And with that, I'm probably way over, and I will call it quits.
Terry, can I ask you just a couple of questions?
I can't quite hear you.
Yeah, can you hear now?
Yes, I hear you better now. Yes.
Yeah, it's just a couple of questions. One is to do with the speed of light, this concept of absolute speed of light. I'm still a bit confusing. So if you take that example of Einstein about the train, so if you imagine two trains going opposite direction, so the passengers on the two trains, when they're crossing relative to each other, the relative speed doesn't go to zero, isn't it? And if it doesn't go to zero, what does it really mean that the light, the speed of light, or either is simultaneously positive and negative and zero, or is something else? That's the first question. And second question is the other hypothesis. Imagine that our planet Earth is fully uniform. It's about gravity. If you dig a cylindrical hole through the planet, so assuming that's uniform, absolutely symmetric, if you drop a ball through this cylindrical hole going through the Earth, so it won't fall out of the planet, so it's likely to go bouncing back and forward, isn't it? So how could you explain that in terms of the space, in the space-time framework, this phenomena? And then you have another case, if you had many cylindrical symmetrical holes on the planet, and if you drop on one of the cylindrical holes, and where it's going to go?
In terms of the framework I've done for the cylindrical hole, which is a fairly famous example actually in that, none of that would change. The gravitational properties that you have still are very much the same at that level that you would get from just the standard expression of gravity. I think both Newtonian, that one you probably get by just with Newtonian gravity model. So yeah, and I think the usual solution is you get the reverberation where it goes all the way through, accelerates on the way down, then gets just barely, assuming no air friction, it gets barely to the surface on the other side, and comes back, and you get this resonance. So everything I've talked about here, none of that would change any of the math on that. I mean, the math we have works. So where I say you want to be careful is in the cases where you go fringe cases where you go like, well, why did this system slow down and that system didn't slow down? So I don't think you see a change in that. And I'm sorry, could you maybe briefly repeat the first question again?
The first question was about the speed of light. So I was wondering, and I get confused about it, that you can't multiply the speed of light. It remains same. It invariance of the
Right.
speed of light, that basically which I'm questioning. This invariance is to do with the fact that the speed of light is simultaneously has got an absolute value and a negative value, and at the same time is zero, or is something else. What caused this invariance?
You may be referring to some stuff. I'm not familiar with that. The one comment I would make on it, that the speed of light, it is useful to recognize that speed of light can vary with the reciprocal relationship according to the relativistic Doppler factor. And of course, that's been known for a long time. That's why Einstein would not define the speed of light without a closed loop. He just recognized that you can't do it. No one's ever come up with an experiment that actually succeeded in doing that. And it seems to be a fundamental characteristic. So there are difficulties in the speed of light. The only assertion I would make is that anytime you measure a loop, you will get a very consistent definition of speed of light. But that's not necessarily a good definition of the underlying physics. It'll be more complicated going on.
Yeah, it's fine. Yeah, thank you.
Thank you.
I'd like to get a little bit more clarity on the Schrodinger's cat and its relationship to time. Is there some material in writing that I can find?
I'll do an expanded notes write-up on this one. We'll add some additional material. The figure that I showed, though, in which I was emphasizing the cat following classical physics within that bubble, that is very much a result of the concept I mentioned, that observation is extremely simple, extremely common, and is nothing more than acceleration. So if you follow that premise, that there's no need for consciousness, no need for anything, that it's actually just a very simple bumping process that's local, then acceleration winds up inevitably collapsing the cat into one state or another. And one of the reasons why we have pondering or mysteries about that is we have mathematical expressions that just infinitely extend out the quantum wave function without recognizing speed of light limitations on it. And I just don't do that, because just like those diagrams I said, when you create a new particle, any real quantum mechanical experiment starts with an actual particle, then goes into a quantum state. And I know people can do games, they do mathematical games, say, yeah, but it's all part of one gigantic wave function, blah, blah, blah. But that's not what we actually see. That's not what we actually observe. What we observe is if you put a particle in a certain situation, it starts behaving like a wave. And it's not a complicated thing, but in doing so, it's also strictly limited by the speed of light, and it's constrained. So what I'm suggesting is a lot of the math where we talk about universal wave functions just is not correct. It's a fantasy that has been created by exploring too many chaotic implications of what's actually a rather small number of bits. And that we have is a much more real present moment state machine type of universe, where when we talk about the present, some people would say the present is illusion. I would go in the exact opposite direction. I'd say that the present is very much real, but it's also complicated because of the way we're broken up into inertial frames. I don't have a good reference for you in that, but my perspective is coming from that. The other side of that is I'm saying that the cat would live or die because it's self-observing literally from the atomic level up. It's not even close. It's just incredibly classical. But information is the token, is the exchange fund, is the exchange item for space-time. So if you can exchange even a tiniest bit of information about the location of the cat, then you wind up crystallizing that cat into a small location. This is not linear. This is extremely nonlinear. So you have this ability to localize that cat. But if you can keep the cat information isolated from the universe, which they can do with molecules up to the size of, I think, about 4 DNA units, pretty big molecules. It can keep those sufficiently isolated from irreversible information loss that they will double slit interfere. That's telling us something. I mean, that's a complicated molecule that has internal state. And I would say that's an argument right there, that molecule, you can define one state as alive, one state as dead. You can watch it interfere and say, well, did it die or did it live while it went through the interference? And you can say, yeah, this one died, that one lived. So that would be a real life experiment that would address what I was just saying about the cat either lives or dies. I think we've got an enormous amount of confusion about internal state versus spatial superposition. That's one of the distinctions I'm trying to make, is that information isolation is so difficult that it's easy to overlook the power of the space of the information isolation. But when we do that, then you get some very strange impacts on space-time itself, but not on the system itself, not the system internally. Don't know if that helped in the answer. Or did.
Thank you.
Okay.
Food for thought.
Hello, my friend Dr. Aliman has a question.
Yes.
So it was very interesting to hear about this novel idea that space-time may emerge from matter at hadron scale. So it seems that there are certain illusory processes going on. And so I was thinking, what if instead it would be that space-time emerges? That's a very speculative idea, but just to see how we could experimentally problematize these two conjectures. So the first one was that space-time emerges from matter at hadron scale. The other one I was thinking about is, what if space-time would emerge from living matter at Planck mass scale? So there we have biological cells at that level. How could we actually, do you have an idea on how we could investigate this? Could there be a possibility to make it problematic by experiment?
Well, one comment on the emergence of space-time from any kind of material system. The explorations that have been done in recent years on like very high energy gamma rays have shown that Lorentz, the inertial frame symmetry, apparently extends just to infinity. No matter how fast the system moves, it can always conjure up the same physics that we have right there. So in some sense, that is, I think, some experimental verification that at the very least, this has huge limits. Every bit of physics that we've explored shows that when you have like a spaceship or you have some module that's traveling, they just see the same physics. This is just exactly what Einstein postulated. It is, to the best of my knowledge, what we have seen in every case, including those more recent gamma ray experiments. That's just what we see. And I would argue that is in some sense an argument for attachment of these metrical systems to the matter itself, simply because that's all we observe with a given material system. And where you could go at it experimentally would be pushing at those edges in which the definitions of time start to diverge. The idea that you accelerate a system and suddenly at one end of the system, you literally have a gap in time and say, well, I only experience this amount of time, but you're saying that for my physics to start working right, I have to use this definition of time. There's something there that could be explored. And I think experimentally that could be an interesting topic. In terms of biological systems, first, I should emphasize that I don't, the entire Planck domain, I just discard as noise. Wheeler made that interesting postulate. It was based on infinitesimal, infinite space-time definition, as you just saw. That I just discard as noise. It's interesting noise, but I also think it wound up just setting things back. The Planck scale doesn't buy you anything. But in terms of your question,
Planck mass scale, I said.
I'm sorry,
The
what?
Planck mass scale, I
Yeah,
said.
that's what I'm talking about. The Planck mass scale is something I just would tend to discard that as energetically impossible and not actually part of the physics that we're seeing. Wheeler's speculation, and it was just a speculation. We had lots of interesting speculations. But on your biology question, if I couldn't, I think that actually is an interesting question. If material systems can create their own definition of space-time, why can't biological systems create their own local small definitions of space-time to use for calculations such as biochemistry? When you look at the emergence of order from some of the small biochemical systems, where you just get a total chaos, and they pop up with some kind of result where you have extraordinarily high reliability. This is what Hopfield studied in his 1974 studies, which for that, I think he did deserve a Nobel Prize. But that's fascinating. And I think this idea of little miniature versions of space-time, maybe tweaked a little bit, could be a real research topic for doing something like that. What I'm saying about Planck scales, I just don't think that's necessary. I think that's an unnecessary complication for doing that. All you really need are just the molecules playing some games with the energy levels that are already available to them. As soon as you go up to the Planck scale, those are huge, huge energies. And the Planck
But is it a coincidence that we have cells at Planck mass scale?
I think it is. I don't think there's because the cell, for instance, one thing, the cell range is absolutely enormous. You have these the cells and on like some of the fairy flies, the incredibly tiny cells in some of those. You have gigantic cells. The range of cells is I don't know how many orders of magnitude. So I would suggest that probably is a coincidence. But I base that more on the thing that I just don't think.
Because yeah, I've recently heard that a string theory allows, a certain version of it allows a hidden dimension at micron scale. I've read it recently.
String theory has many dimensions that you can come up with that. And yeah, and you can go this route. So obviously from the perspective that I'm coming from, since I'm using this sparse perspective, anything down the Planck scale is just doesn't pop up. So that's the analytical perspective I'm using that. But at the same time, on the biology question, I think that's an interesting question, but I think going to Planck scale and going to string theory, both are probably more noisy complications than they are actual getting at the issues. I think if we just look at it in terms of very mundane issues of momentum, of angular momentum, of relationships, and have a better understanding of how space-time works, I think we come up with some interesting low energy answers. So, but I think it's an interesting idea that biology is playing games with this idea of creating space-time.
I have a couple of questions. Terry, I'm Ravi Sharma.
Yes.
If you would permit, I will start. First, I want to start with the basic concept of space and time. Do you ever think that space and time both could be discrete, like quanta, in terms of quantum field theory? People deal a lot with space being quantized, but not a lot with time being quantized. Second observation is, I do like the question that the previous questioner asked, that at hadron scales or scales smaller than BSM particles like partons, resonances, there the string-like qualities of space might work. And there are indications in some ancient studies a few millennia ago that seem to suggest string-like constructs before you see mass emerge. That's just another observation. So first one, discreteness of space and time. Second, at very, very small scale, string-like breakup of space-time, especially space. Third is, do you think that scales of space and time are consistent from very, very micro to very, very macro? Or do we have to change our concepts of space and time when we go from very small to very large? I will stop at these three and ask again, if I have time, to ask more questions.
On the issue of granularity, I do strongly agree with the idea that things are broken up into discrete packages. So for instance, the example I usually give is fermions. I think protons and neutrons are a very good example of a discretization of the underlying physics. If in terms of a grid type lattice network, that I don't go. And the reason is that those are hyperclassical concepts. Those are ones where you have already an existing predefinition of space, of a lattice of two-dimensional space. A lattice theory is very useful in quantum chromodynamics. I remember when it first emerged that it was used to calculate some results that they couldn't do before. But I think the model kind of overtook the particle, and people just started saying, oh, well, space-time is a lattice. And then they started looking for that, and all the experimental evidence is against that definition of a lattice of that. So if it's a lattice that presumes dimensionality, no, I don't go that way, because I think you wind up having versions of infinite information if you do that. And that to me is a huge warning sign. Anytime the information starts going to infinity, where you start saying it's infinite information, you're almost certainly going down a dead end trail. But discretization, yes, that there's a packaging on that. Remind me quickly, second one was the
scale from very small to very large was the third question.
Okay, I'll address that one. Third question, if you go with the model of matter generating the space-time, then you do wind up with there very definitely is a definition, a difference in scale. The scale that we have seems to be emerging from the particles, and those particles get into some kind of an agreement with each other by exchanging information. That agreement helps define this definition of space and time and going parallel. And I think it's a very interesting agreement. I think there's experimental possibilities of that maybe there's some flexibility there about how this agreement comes about, especially in small systems. But you get scale emerging from the particles that have this consensus agreement. You know, why does every electron have the same mass? There's some kind of massive agreement in place there that transcends our usual ideas of space and time. It's something that's not just make a bunch of electrons and throw them out there. There's something, you see that in quantum mechanics, that two electrons in the same place can't tell each other apart. So there's something much more interesting going on with these.
Well, it is related to the comment you made on provenance, that you just cannot define space with and time without reference to the original version from which they transformed. Remember your slides stating that you have to remember the history of how you got there.
Yes.
So that is definitely borne out by a lot of deep studies. We can go into them some other time because everybody may not be interested. But an electron, for example, remembers
Yes.
the rules of where it can exist with other electrons and how many other electrons or not exist because of its provenance, its history.
And from that really is where you get the emergence of concepts of rulers of space, of time. The Pauli exclusion is just a marvelous little, I won't call it a side effect, but it's certainly a fascinating emergence from this fighting that the half-spin fermions go on. Half-spin's been discarded as just a given, and we need to not do that. Whatever's going on with half-spin is probably one of the most fundamental features of the universe, and we need to understand it better with that. Your second question was about strings, and strings emerge, and the smallest strings I know of are the strings inside of protons and neutrons, and those are the gluon, the forces that bind them together. They are strings. They are absolutely strings. They behave like strings. They vibrate like strings. They give resonances like strings. They produce excited versions of protons and neutrons like strings. And they are the origin of the current string theory. Only the current string theory took it down 20 orders of magnitude and completely disconnected it from the rest of the world. And in the proton version, you have real particles, you have real forces, which again, you can translate that. But the point is, they're like little bolas. They got little balls spinning on the end of a string, and the string is vibrating. There's absolutely stringy stuff going on there. I find it remarkable how little the superstring, the original name for what's going on now is called superstring. String, that was the original.
Yes.
Yeah, and it's superstring theory. They don't talk about that much. There's one physicist who did.
Frank Wilczek used to talk, but he has slowed down talking about it. He started his QCD based on that aspect a little bit, but now he doesn't. So I agree with you. But anything in the BSM, beyond standard model, the space of colliders and experiments, the strings are playing a little bit increasing role. So is statistics, so is AI, and so is quantum information. But I like to support you on the fact that the particles are not point-like, that they have structure, that their structure is what probably determines the kind of space and time that we are talking about. So I agree with your thoughts on that. I have one question. At very small scale, why can't you treat the space as affine space, AFFINE, where you forget the origin but keep everything else the same from one dimension to another? Multidimensional.
I think you or someone asked me that earlier. In fact, I was trying to find it.
I asked you in that chat. They were inviting earlier questions. I asked you on that.
Okay, I got a little lost on where I found what when.
Yes.
Too many social media going at once. Affine spaces, I think, are a reasonable approach on dealing with some of this, because they do essentially strip out some of the additional structure that we impose on it. So exactly how, I don't know, but
well, I have a paper coming. I will share with you.
Oh, okay, good. Sounds good. I think John Baez worked with affine spaces some years ago. That was my main interaction about that.
Would be interested in learning about that work as well. But my paper should be out in a couple of months.
Okay, Sounds good. Anybody else? I think we're over time.
So actually a question from George. What is the length scale of an electron?
Length
Very good.
scale of an electron. Of course, that is an electron is an asymptotically point-like entity, meaning that if you add enough energy, you can always make it smaller and never wind up seeing any structure. Superstring postulates that if you went really, really, really big, like with an accelerator the size of the galaxy, you could see structure on the electron. But I'm inclined towards the definition of electron as being truly asymptotically point-like. Other than that, Compton wavelength is about the best you're going to do for trying to define a diameter, and that's rather arbitrary. But I think the fact that it's asymptotically point-like is really interesting, and I would even say it's connected with the definition of time. So I'm following a little bit on that, and that seems like a strange statement, but electric field in general, electric charge, and electric charge with time, colored charges with space. Think of that as a possible association. This is going a little bit on the Piotr's work, but there's some
Yes.
reasons why electrons are the particles that just kind of go with time. They like time. They're compatible with time. They're part of the overall consensus of the universe with the definition of time. Protons also, because they also have pure electric charge. But if you're talking about quarks are little stubborn little cusses. They say, no,
Different.
I want to go that way. I want to go some other definition of time. I want to go this definition of time. And I think that's why when Piotr talks about protons having a different definition of space and time, that's partly what he's getting at, is that there's weird stuff going on inside of a proton, and it's not just weird. It's weird.
The topological work of one of the attendees in this conference, who is not seen anymore, was Jarek Duda, who has done a lot of topological description of particles, non-point-like topologies. But now in my interpretation of the paper that's coming out, electron does have a structure, and its structure is related in a way to how it is coming out of nucleus. Its origin is in nucleus. The second part is that not only it has a structure, photon also has mass. Those are some interesting consequences of the theory I'm working on. I mean, that I have published. It's accepted for publication, and I will share with you. But these are interesting things. I'm just one more quick question. Type of interaction. I'm talking of gravity as being one, electromagnetic being another, and so on, and maybe the neutrino space being weak, another kind. So are these different space-time types, or do they exist in one space-time continuum?
Actually, I would be inclined to agree that they are showing aspects of different features of space-time. So
yes,
in the case of quarks,
thank you.
are little cusses that want to go off and constantly adamantly want to go off on their own definitions of time that are orthogonal to our definition of time. And then causality comes back and says, you're not going to do that. And they wind up getting jailed for it. They wind up getting fined, but the jailing is very useful because then you wind up with these things called protons and neutrons that are compatible with the definition of time. So then you have that matched up with the electrons. Now, in terms of electrons, there's a structural aspect to electrons in terms of the charge, that even though we think of electron charge as one unit charge, I'd say there's a strong argument that even that charge is actually composed of three Rishon-like orthogonal dimensions. And they're not actually Rishons. You can't make the Rishon concept work completely self-consistently until you make it into orthogonal dimensions. Then it works. Then you can find some definition with that. And there's some kind of relationship, and there's some kind of a structure with that.
I will take later with you, if possible, one-on-one, other properties of particles such as spin charge, color charge, and all of those things are how those are related to space. And that's a long discussion. Perhaps
That's an
today we,
interesting
yeah.
discussion, because spin to me is
But your slide does touch on that.
yeah, until the universe invented spin, the universe didn't, this is that underlying universe had to come up with spin, because until that spin is essentially self-observation. It's angular momentum. And remember, going back to that comment, that momentum, acceleration is observation, then spin is self-observation, because it is a constant acceleration. And I really think this just whole idea of units of spin is could be worked out to be literally how the universe finally got to a point where it could emerge from this nebulous version of whatever that underlying physics is. And it's kind of like, oh, this is cool. And you get these little self-observing entities, and then things start popping after that point. So I do have a paper on my website where I talk about, I think it's just cubes. Cubes are fun or something like that, but I talk about Glasshow's cube for organizing fermions, and how that gives the interpretation of rishons as orthogonal dimensions. Really, it's amazingly powerful for mapping out all the fermions. They all just become the bridges between two cubes on a tesseract, and that's it.
Yes.
And
The very fact that you mentioned tesseract, we have come to dimension 4. We'll take you to dimension 7, and some modern physicists have gone to 11. So that is another aspect we can discuss sometime.
Okay. Sounds good.
I just want to thank you.
Well, thank you.
I hope, I think it is Devabrata's turn to thank everybody, but I certainly as a participant want to thank you, Terry, for a delightful talk, and to all these colleagues of ours who are listening and participate.
Thank you.
Terry, sorry for coming back. I found your lecture or presentation very, very interesting, and I'm learning quite a lot of things. Just going back to the question of the associated with a bit of fundamental physics about the Big Bang. So if we think that Big Bang occurred and the space, time, and the matter were created at that instance of Big Bang, what was the nature of that singularity in the time of the Big Bang? That it's in terms of nature, I'm trying to describe it, whether it had a mass, had a matter, or it wasn't a matter. What that singularity was about, effectively, in terms of nature, physical nature.
The direction I would go with that is in keeping with, there's been some really interesting work lately by Boyle and Turok, Latham Boyle and Neil Turok, about dual universes. And I've been a dual universe person since 2007. Chen and Carroll came up with the idea in 2004. You could argue some other works go back even farther. But Boyle and Turok, those are the ones that I think they've even made some predictions about 36 scalar fields that my interpretation is they correspond to those obnoxious quarks on the families trying to escape the definition of time. But the 36 scalar fields are needed to cancel out and produce. It's a very different mathematical framework trying to cancel out space-time singularity or space-time mass. But I think they're onto something there, and they have a softer emergence of these dual universes. Turok, I think, leans towards thinking that one of the universes kind of overlap like a mirror. They've gone back and forth on that thing. I definitely tend to go towards actual literal two universes, and I time down even closer to the other universes composed of what we think of as the weak force blind chiralities of the fermions. and that our universe is the weak force aware versions of those fermions. But both sets of fermions occur in both universes. It's just which one dominates. And if you follow that kind of math, it's a softer origin. It's not a point-like singularity. It's something more like a consolidation of agreement in which a whole bunch of little things kind of get together and they join hands and say, wow, if we all decided to do this and put our fingers together and define a dimension, look how much longer we could hang around and do things. And I think that's kind of where the universes have their origins, more like a consensus agreement. And the consensus produces what we call time, but time in two directions. You got time going this way, you got time going the other way. Geometrically, they're both causal time. Neither one of them is going into the past, but geometrically, that they decide to go in opposite directions, which is where you get your cancellation of the protons. People worry about that. This stuff looks like antimatter, but it's not, because it has negative energy. So contramatter is what I usually call it, but it's matter that we see. It's already in the standard model. And the reason it can't see the weak force is because it's going the wrong direction in time. So it's going backwards and it says, I'm sorry, I can't do this. I'm going the wrong direction. But the net result of that is also called the Higgs interaction. So that's where we get our emergence of mass, is this competition
Yes.
between these two different spins, or two different chiralities, not spins. These two different chiralities. And it's just a fascinating thing. I think there's a really interesting. I keep hoping I can convince Boyle or Turok to at least consider the idea of a sparse interpretation, because I think they're doing great math, but I think they've got it. I think the use of infinitely smooth manifolds is actually holding them back a bit, and I think they could do more if they would focus on the idea the vacuum is just a vacuum and the particles are doing all the heavy lifting. But I would recommend that as a good. That's the best description I've seen, is the Boyle and Turok work on dual universes, which I think is, like I say, they actually made a prediction about these 36 things. I haven't seen too many people do predictions about anything these days, so it's good stuff.
Thank you. Thanks.
Robbie?
On that point, there are theories that believe in multiple universes and also in local Big Bangs, but not a universal Big Bang. So if the matter energy from their origin to their end, whatever that end is, have consistent rules, then it is like that agreement that you are describing, because they are following same rules,
Yeah.
whether they are however sparse they might be and however dense they might be in some regions.
Yeah.
So
Yeah, I think
universality of rules determines the similar or same behavior, except at pathological points like black holes or like local Big Bangs, where physics has to be modified, just like we do for high energy particle accelerators. And that is the point which I will discuss with you one-on-one later. Thank you.
Yeah, and the brecciated universe figure is kind of hinting at that idea that you get. I think this idea of consensus is just a remarkable idea. You can see it, we see that in nature where things just suddenly crystallize, just they go. And I think there's an effect going on, and the crystallization that's needed is time. When you get enough particles that get together and say, if we have our own direction of time, we don't just have to go back to formlessness. We can go out and shoot out there for a while and go out and do something. And persistence persists. So they go out and they do this, and you can get and this is where I think the physics could get really interesting, because if matter defines space and time, there's got to be some experimental directions with that about.
Some mathematical and astrophysicists, Terry, have postulated that time enters like in 11th or 14th dimension, according to them. There are papers that I quote in my already published paper.
Hmm.
But those are other physicists doing that or astrophysicists doing it. I've read about them.
I know, so even on my own, like I mentioned, the tesseract encompasses the first family. But if you have all three families, you're going to have to go at least up to 5 dimensions. So you get some the criteria I always use though is this: orthogonality is unbelievably expensive, and I think
Yes.
it's a good heuristic because when you just go around and this is the problem I have with Hilbert spaces. Hilbert spaces just treat orthogonality like it's completely free, and you don't see that in the actual demonstrations of orthogonality in, for instance, wave mechanics. I mean, they're just radio waves. Orthogonality costs something. You have to have a definition where you distinguish those dimensions from each other. And assuming dimensions as a given, I think is just a dangerous idea. You want to work for them. You want to say like, okay, if I got to add another dimension, there's a cost. It's going to be a steep cost, but it doesn't mean I can't do it. But it does mean that I have to pay that cost. And this goes back to my general, too much of our math is based on 1700s concepts that had no idea of quantum mechanics, no idea of relativity. They treat the speed of light unconsciously as if it's infinite. They treat the cost of information compression as if it's zero. They have all these things where they just don't care about the information and the mass cost. And that's my other criteria. So if you start proposing infinite information, watch out.
Too much dependence of QFT, quantum field theory, on Hilbert space, one way or the other. And I don't know how to untangle that, at least not at present.
Well, the quantum field theory, and this is, if you've seen that presentation about the Casimir's statements, where he said that simultaneously we see the effects of these wave suppression effects between the plates, but also it never exceeds the energy of bonding of those plates if you tore the plates apart. He's saying something really important with that. That's a paradoxical statement because it's saying that if your quantum field theory predicts those wave suppression effects, then the fact that it's equivalent to bonding says, and the total energy driving those effects is the energy of bonding from the local matter that you have in place. Now, that's a remarkable statement. That's completely different from quantum field theory that just puts it all out through space and spreads those oscillations everywhere and gives them no limits. So it's a very different approach in that. Now, people do that because, you say, well, but, obviously photons travel through empty space, so they got to be traveling on something. That's the temptation. And I think that's where we go wrong, is we're going like these relationships are taking place in some scale, in some kind of relationship where there's a distance relationship, but it's not the one that we're used to.
Yes.
It's and I say I think there's just some great physics hiding right in plain sight, and we're not exploring it because we're using tools that are frankly too old. They like I say, 1700s continuum math presumes too much about information, presumes too much about speed of light, presumes too much about density, and we need to tie it in more tightly to what we're seeing.
Thank you.
Thank you.
Hello.
Hello.
Hi, Dr. Sharma. This is Mr. Ghoshal, Devabrata Ghoshal.
Oh, thank you.
I'd like to invite you for your own presentation soon, whenever possible.
In 2 to 3 months, I'd be ready. Because then my paper would be published and I can freely talk about some of these ideas.
That would be great. Thank you.
The publisher says if I talk too much beforehand, then they will not publish.
Okay.
They will publish, but they have just printing under their control. They have accepted, but they have to still print it.
Okay.
It's an old-fashioned journal.
Ravi, I agree with Deborah. I'm looking forward to seeing your papers, so that'll be good.
Thank you, sir.
Thank you.
Thank you so much. Devbrata, thank you for organizing such a wonderful lecture. And I hope there will be a few in this series and few by Terry himself again.
Yeah.
Thank you.
Yeah. Mhm.
Great talk and very complex. I think on one slide I could spend an hour studying sometimes or more. Thank you.
I think I kind of overdid the density in the slides this time because I've written papers about some of those individual slides. That tells me that's a warning. I probably need to spread it out.
Yeah, fantastic. Thank you.
I have planned to.
I just might interject and inform our remaining participants that I have worked on Apollo program for 5 years or so and received NASA Apollo Award. So that is the external space aspect. And then I'm a particle physicist for my PhD and other work. So that is internal space to say micro levels. Thank you. There was very interesting question the lady asked on macro-micro relationship, but I do not know about the Planck thing, but there is some kind of continuity of laws that get transformed when you inject life or life-like structures, such as proteins, into matter. And I, as a physicist, only know about matter and energy, not about the addition yet. We will learn and we'll talk about it some other time. Leon, that is for you.
I think we had a question from Dev.
Yes, Dev, can you unmute and ask the question online?
Hello.
Oh, now we can hear you.
I have a question. Maybe agree with this, but recent experiment is already done about the entanglement, that quantum entanglement, that Bell inequality is violated again and again. Even they have tested under this Bell inequality under the relativistic constraints. Then they again find that this Bell inequality is violated. Means something super luminal connection has been established, but statistically. Then I could not understand that how this happened. Why this Bell inequality violation occurred statistically? I know it's a statistical measurement. Then what would you say about this? If it really violate, then certainly see it put question mark on velocity of light. Then if it would be possible, then the whole structure of special relativity, general relativity will be collapse some kind of that. What would you say about this?
On the Bell inequality, and I have a little short, very short, just little paper essay about. I am in a unique category that I don't believe in any form of extra light communication, even for entanglement. And but at the same time, I absolutely believe Bell inequality has been violated, and I think this marvelous work is extremely real. It's just that the constraint that people tend to forget, sometimes they bring it up, sometimes they don't, is that you never get a Bell inequality until the speed of light criteria has been met. Until light comes out from the signal where it was done one place and arrives at the other place, you don't get the violation of inequality. And you say, well, but that doesn't matter. Well, it does matter if, in fact, nothing changed at that end. Asher Perez was one of the first one I saw that thought from, is the idea that you didn't change anything. The guy at the other end, when you look at an entangled pair, Nothing changed at the other guy's end. And I think that's is in a sense, once you say that that seems pretty straightforward, that there's no actual change, or otherwise you'd be able to detect it. And he can't. There's no difference at that end. So as soon as you say that, that says something extremely strange about what happens when the signal finally arrives and says, here's what I saw. And then you start seeing these statistical emergences of events. And some of them can be pretty tight. And you can make them sort of be like, wow, that had to be correlated just from one event. But you can't, we have to be careful in the interpretation. And this is why I go back that one approach for getting rid of that problem is to abandon the idea that it's a uniform definition of space and time in this situation. You have each has their own definition of space and time, then those two definitions of space and time are interacting. And you can't come up with a resolution in terms of that. We're seeing a phenomenon that is an underlying phenomenon that doesn't match either of those viewpoints. But it's still bound by the speed of light. So the speed of light comes up, you see it, it clicks, you finally hear that, but you didn't change something other end, and that's where I think people go wrong in this. So I even use a phrase, I say non-locality is a meaningless concept. That I guess Einstein would like that, you know. And then again, he might not like the idea of saying space-time is a I don't know. In 1911, Einstein might have liked the idea that space-time was attached to matter, but there's two very different Einsteins. There's a general relativistic Einstein, there's a special relativistic Einstein. They clicked off at 2011. And so I don't know. I think he would like the idea that there's, and I'm quite adamant about that. I used to be really big on the non-locality, and I'm very big on the fact that it exists, and it's absolutely one of the mysteries of physics. But the interpretation that you change something is not experimentally valid because no one ever sees that. You never see any change in any system, no matter what you do, until you get that other signal coming in. Then you see a change in the system. That argues that we're looking at that problem the wrong way. But deep physics, and we need to dig in there somewhere and look at it in different ways. Again, I keep harping on biology, but I think cells have figured some of this out, and we're just not getting the message yet. So, and again, my standard example, if it takes us a supercomputer the size of a building with modern technology to model a few simple molecules that a living organism can take care of them lickety-split, come out with an almost 100% probability of transferring an electron that needs transfer to live, then doesn't that say that we're not understanding very well how it does that? And I think the answer is that. Yuri Manin was the one who first mentioned the idea of molecular biocomputing back in 1980. He immediately got sidetracked, but still he brought up the concept. And I just think we're missing some beautiful lessons in plain sight, and maybe need to poke at them from a little bit different perspective.
Okay, thanks. But still, I don't understand that if when we measure the Bell inequality under the constraints of relativity, then how we can find that it's violate? I could not find the reason behind why this violate under the constraints of relativity. We measure particularly this, I think, 2 or 3 times, particularly this experiment. They measure the well violation under the constraints of relativity. They created 2 setup entangled particle, and they measured their outcome before the light reaching signal from one to another. Actually, in that sense, I am asking. There are many well violation experiments. Some are measured under the relativistic, or some are non-relativistic. Even in India or in many labs around the world, Bell inequality test has been done. But relativistic constraints few experiments are there, and they find it for Bell violation.
Yeah.
Yeah.
So I agree that the violations are absolutely real and very well documented.
Yes, I agree that quantum teleportation is under the constraints of relativity. There is nothing superluminal transfer of masses. But particularly, I am asking the Bell violation test, just that is also a statistical. The quantum teleportation, even quantum internet, all such things are going. China has already teleported some messages from even space. Also, that follow the limits of velocity of light, special relativity. But some experiments are there when they put under the constraints of relativity, then again find the Bell violation. Then I could not find the reason behind that.
So are you referring to any particular papers about special relativistic
Yes.
violations?
Yes, first paper to 2015, the relativistic Bell violation and the relativistic constraint. First paper, or there are other paper also. First is 2015.
I'd like to read the paper. I think I could probably comment.
Yes. Okay. I will send.
Yeah.
I will send definitely. Yes. Okay. Thank you, sir.
Okay. Thanks.
Thank you. That was a deep question.
Anyone else?
Thank you so much, Terry.
Thank you.
I think, Devabrata, we can sign off if there are no questions, or because it's too late, people are tired. Especially in India, it is like
You guys are
1 a.m.
Yes, it's early for you guys. I appreciate you hanging around. I was thinking that because I know the time zone terrible. The difference is terrible.
I'm visiting for winter months, but normally I'm in California, where it would have been a good time. Thank you.
Thank you.
I'll be in touch with you.
Okay.
By email. Thank you.
Thank you. And Dev, I look forward to reading that paper.
Yes, sir. Thank you. Thank you and good night. Thank you so much. I'm signing off.
I'm signing off too.
Thank you for joining. Yeah. We have another one on April 5th.
Thank you.
Welcome.
And I'll be back in June.
Sure. Yes. Send me the topic. Yes. And we'll set up the day and time.
Goodbye, everybody.
Bye.